Today, we are going to see the system programming concept and basic assembler concept. Here, we have assembly level language. In that language, we have two types, that is called as pseudo opcode and machine opcode. Pseudo opcode divided into different types and machine opcode is again divided into different types. What are the different types of pseudo opcode, or what are the different types of pseudo opcode available? Start, end, DC, that is called as a data constant, DS again called as a data symbols, using LTRG, that is again literal organizations, EQ, drop are the different types of pseudo opcodes. Types of machine opcode: register index, storage immediate, register storage, and storage. These are the different types of machines opcode. That means the instructions is divided into two basic types. First is called as a pseudo opcode and machines opcode. Now, the types of registers. We have 4-byte registers, 2-byte registers, 6-byte registers. RR types instructions are 2-byte registers. RX types takes 4 byte. RS types takes 4 byte. SI types takes 4 bytes. SS types takes 6 bytes. Now, how we identify the instructions is RR, whether it is RR types instructions, SI types of instructions, or RX types of instructions. If the instructions end with RR or instructions end with R, then it is called as a RR types of instructions. Example, SR, BR, ALR are called as a RR types of instructions. Now, the instructions end with the R, then the type of instruction is called as a RR types of instructions or register instruction. Now, the instructions end with second type, the instructions end with I, then it is called as a SI types of instructions. Example, LI, AI is the example of SI types of instructions. Now, when we can call RX types of instructions, how we identify the RX types of instructions? The end of instructions not with R and I. The instructions is not end with R and I, then it is called as the RX types of instructions. Example, A and R. That means the instructions end with R, then it is called as the RR types of instructions. Instructions end with I, then it is called as the SI types of instructions. The instructions does not end with R and I, then it is called as a RX types of instructions. So these are the basic concept related to assembler. Now, general instructions format. The general instruction format consists of data, DC, and F5. Data is a label, DC is a opcode, and F5 is a operands. Now, the informations and number of byte taken by that particular H, F, and D, half word, full word, double word, or characters. That means half word takes 2 bytes, is indicated by H, full word takes 4 byte, indicated by F, double word takes 8 byte, indicated by D, character takes 1 byte, indicated by C. Now, whenever we in programs occur DC and DS, we need to take the alignment. What do you mean by alignment, or how we do the alignments? If DC or DS, then add multiple of 4. If we occur DC and DS, where if we get the F, then we can make it as a multiple of 4. If we get H with the DC and DS, then we can do the multiple of 4. If we get D, then we make it as a multiple of 8. How we identify the literals or literal table? First, the value should multiple of 8 if the LTRG occur. What we do? If we get the LTRG, then it should be a multiple of 8. Always it should be a multiple of 8. Now machine code. If we get the RR types, then value, value 2. Then opcode instructions are value, value 2. If we get the Rx value 1, value 2, then Rx value offset x comma b. How we calculate the offset? Value of symbol minus content of base. If we get the SI types, then value, offset and base. Now, BNE always equivalent to BC7. BR is always equivalent to BCR 15 and 14. Let's take one example. For the following example, we have to draw symbol table and base table. For the given code, we have to first find out the LC. LC is called as a locations counter. First, the program start with the John. Here we will take the LC equals to 0. It is a pseudo opcode, that's why we have take it outside 0. Now, using it's again called as a pseudo opcode. That's why here we have 0 take as the outside of LC. Now, L is the instructions. For that, the previous locations is 0. That's why LC start with 0. That is location counter is first 0. Now LC again takes the 4 byte to store the instructions. So next instructions take the 4 bytes. So the locations counter is 4. Now A is again takes the 4 byte. 4 plus 4, 8. ST location counter is 8. Now ST is again takes 4 bytes. Now the locations counter will be 12. Now here we occurred DC and DS. Whenever previous, as per the previous instructions, whenever we occur DC and DS, it need to take the alignment of that particular. Here we have the F. So F is according to conditions. Here F is a multiple of 4. So 12 is a multiple of 4. Obviously, that's why 12. DC, again DC takes the 4 bytes, 16s. Now we make alignment of that particular pseudo code. 16, 16s, yes, it is a multiple of 4. Now 20, yes, it is again multiple of 4 because here F is given, and end with 20. Now, first we draw the symbol table. Symbol table containing the 3 most important fields: symbols, value and relocations. First, identify the different types of symbols available in left hand side. So John, 4, 5, these are the 4 symbols. Now John, what is the value of John? 0. What is the value of 4? 12. What is the value of 5? 16. What is the value of 10? 20. Here we have to take all the values of symbols. Now, relative locations, all are the relatives. That's why here we indicate the R. Now, how we calculate the base register or how we draw the base tables. Base table consists of 2 fields. First is called as a registers number and second is called as a container. How we identify the base register? Base register we can identify with the help of using tells the assembler what is my base registers. So what is here my what is my base? 15 is a base register, and what will the content of that 15? 0 is the content of that 15. So in this way, for given assembly level programs, we have drawn the symbol tables and base tables.